All right, so we are going to talk a little bit about polynomial functions. And we have this big, long definition here when we talk about polynomial functions. And you don't really need to worry so much about that definition. It's just a standard, a general way that we can say that, hey, we've got this function and it's in descending order. So if we had like 3x to the fifth, we might have some 7x to the fourth plus 5x cubed, right? And so all we're talking about is we have a highest power and then n minus 1, n minus 2. It's going down a step each time. So looking at any sort of polynomial function, like f of x equals 3x squared plus 10, that's a polynomial. We have a highest power, and then we have a constant term. So we're going to refer to just this short version of a polynomial function here. And the way we can write this, or the way we can think about this, is we have a leading term. So a sub n x to the n power is my leading term. The degree here, it has a degree, which is the highest exponent. So when we talk about the degree is n. And then it has a leading coefficient. So the coefficient in front of it is just a sub n, and that subscript is just saying, hey, that's the coefficient which goes with the nth degree term. And then the other thing we want to make sure we know about is that we can have a constant term. And the constant term in a polynomial is always going to tell us our y-intercept. Okay, so we need to be able to identify the leading term, which is going to be the highest power. And that highest power we call the degree. And then every time the leading term is going to have a leading coefficient. So let's look at some examples here. We could have a constant polynomial. An example of that might be f of x equals 3, right? Or y equals 3. How many x's do we have? X to the 0th power. We don't have an x at all. So in this case, the degree is 0. The leading term is the only term which is there, 3. The leading coefficient is the coefficient of that term, and that term is only a coefficient. And then the constant, the only term is the constant, so 3. So that's a little bit redundant because we get the same value every time. But we can look at some other types of functions. So we could have a linear polynomial, which we're pretty familiar with dealing with. G of x equals 1/2 x minus 8. So there is no power here. I'm just going to rewrite that back up there. In this case, there's a little invisible 1. So my degree is 1. My leading term is that whole first term that we're looking at, 1/2 x. The coefficient of that term is the number in front, 1/2. And then we have a constant, -8, which gives me an ordered pair 0, -8. And we can continue making this list all day. We could think about a quadratic polynomial. Something quadratic, -x squared plus x. So the degree, my highest power on this one, is 2. The leading term is -x squared. And the coefficient, the number in front of this term, is -1. And if we think about what our constant term might be, there is no constant term. So the constant is 0, which creates a y-intercept of 0, 0. So I've written j of x equals x plus x squared plus x cubed. So they're not always written in descending order. And I want you to notice that 3 actually shows up here at the end. And we could rewrite this. We could say this is the same as x cubed plus x squared plus x plus 0 if we wanted all of our terms in descending order. In this situation, the degree is 3. The leading term is x cubed. The coefficient in front of that is positive 1. And again, we have a constant of 0, 0. And let's just do one more. Let's look at a quartic example. So k of x, and k of x here maybe equals 3x cubed plus x minus 8x to the fourth. So writing that in descending order, that would be the same as negative 8x to the fourth plus 3x cubed. We have no x squared terms. We have 1x and 0 constants. So this is a function of degree 4. It has a leading term, negative 8x to the fourth, leading coefficient of negative 8. And it just so happens, again, we have a constant of 0. Okay? So that is a leading term. And it's really important that we can determine that leading term because the leading term helps us understand end behavior. So what we know is that odd degree functions have opposite end behavior and even degree functions have the same end behavior. So odds have opposite, evens have the same. And if we consider the leading term of a polynomial, we can determine the general shape, not the exact shape, but we say, hey, we have an idea of where these ends go and what's happening to this polynomial. So if the degree is odd and my leading coefficient is positive, so positive lets us know it's going to be rising. So the leading degree being odd, we're going to have opposite ends. And then positive lets us know that it rises from left to right. So we have some function that starts low and ends high. And we don't know what's happening in the middle, but we know where the ends of my function are going. So similarly, if we had odd, which tells us opposite ends, and we give it a negative leading coefficient. So negative is going to let us know it's going down or it will fall from left to right. So we're going to start high, positive infinity, and we're going to end low, negative infinity. All right, so we can also have even degree. Even degree lets us know that we're going to have the same ends. And if my leading coefficient is positive, that would let me know that they are both going up. So same ends, both up, my graph is going to have this shape. Both of my ends are going to be pointing up to positive infinity. And then lastly, we could have even degree, which lets us know same. And then a negative leading coefficient. And a negative leading coefficient is going to mean that they're both going down. So my function's going to go down on either end. I don't know what's happening in the middle. There's any number of waves, oscillations, however you want to refer to it, but we know where the ends are going. So continuing here, we have another example. Given this function, we need to state the y-intercept and describe the end behavior. So, in order to talk about the end behavior, we look at the highest powered term. My leading term is 5x to the 7th. The degree of this is 7, and my leading coefficient, LC means leading coefficient, is positive. So because we have an odd degree, that's going to tell me I have opposite ends. And because we have a positive leading coefficient, that lets me know it's going to rise or go up from left to right. So I know the general shape of my graph does something like this. So it starts on the left pointing down, and then as it goes across the page, it rises to positive infinity. And then, of course, the y-intercept comes from the constant term. So my y-intercept is 0, 15. Okay? So what would you need to state? On your homework, you'll see little gestures that look like this. Multiplicity is the last thing we're going to talk about in here. So when we talk about multiplicity, multiplicity is the power or the exponent on each factor. So when we think about dealing with polynomials, and we've dealt a lot with quadratic polynomials, we try to factor them into linear factors. So if we look at that exponent on each factor, it's either going to be an odd or an even value. And if that exponent on the factor is odd, the graph will cross the x-axis. And if the exponent on that factor is even, we will be tangent to the x-axis. And tangent means it's going to touch and bounce off. Okay? So tangent versus cross. So odd multiplicity means cross. Even multiplicity means tangent. So we'll look at this example here, and it's already written in factored form. So the first thing we're asked to do is identify the zeros, and zeros can be determined by setting the function equal to 0. So I have x cubed, I have x minus 5 squared, I have x minus 7, and x plus 6 to the 32nd. So I have 4 factors here, and if you notice, my table I've made has 4 columns. So I've kind of set this up as a graphic organizer. You don't need to make a table and write all of these pieces of information down, but we're going to write it down so that we understand what we're doing. So for the first factor, x cubed equaled 0, that gives us a 0. If we solved that for x, we would get x is 0. So I know I have an x-intercept at 0, 0. But now we want to talk about the multiplicity. And the multiplicity is the exponent on that factor. And the exponent on that factor is 3, which is odd. So an odd multiplicity means we're going to cross the x-axis at 0, 0. So my blue factor, x minus 5 squared. If I take x minus 5 squared and set that equal to 0, solve for x, I'm going to get x equals positive 5. So since x equals positive 5 is a 0, that means my x-intercept is at 5, 0. So we go back in here and we talk about the multiplicity. Multiplicity means the exponent on each factor. And in this case, my exponent is 2. So 2 is even, which means we are going to be tangent to the x-axis at 5, 0. My purple factor, if I set x minus 7 equal to 0, I'm going to get x equals positive 7. So if x equals 7 is a 0, 7, 0 is the ordered pair of the intercept. Now, zoning in here and looking at this factor, what is my exponent? And there is no number visually that we can see, but we know there's an invisible 1. There's one of those factors. So in this case, we have an odd multiplicity. Odd multiplicity means we cross the x-axis at 7, 0. And our last factor written here in red, x plus 6 equals 32. X plus 6 to the 32nd power, x plus 6 to the 32nd equals 0. So solving that, I would get x equals negative 6, which means I have an x-intercept at negative 6, 0. Now, what is the multiplicity? The multiplicity here is 32. 32 is an even number. So that means we are tangent to the x-axis at negative 6, 0. So the answer that we would be looking for would just be this last row, what our behavior, right? What happens at the x-axis? All right, so we either cross or are tangent to the x-axis at these values. And we have one last example to talk about here. Here we have a quadratic function, so we've been dealing with these all semester. Given this function, let's state the zeros, the x-intercepts, the multiplicities, and the behavior. So we know how to factor this. We know how to graph this. This was from our last unit. But if I want to find the zeros, zeros mean I'm going to set the function equal to 0. So I have 0 is x squared plus 2x minus 15. This factors x plus 5, x minus 3, and I get x equals negative 5 and positive 3. These two values represent x-intercepts. I have two x-intercepts at negative 5, 0 and positive 3, 0. And so if we go and talk about their multiplicities, what is the power on each of these? The multiplicity on both is 1, which is an odd value. So what we know is we're going to cross at both x-intercepts. All right, so we know our x-intercepts and we know that we're going to cross. And if we were going to graph this, we would get a parabola opening up at those two zeros. It would look like this. It'd be crossing at negative 5, 0 and crossing at 3, 0.